Okay. When we talk about strong electrolytes, these are, of course, strong acids, strong bases, and we recognize the strong acids as what we call the strong 6, which are HCl, HBr, HI, HNO3, HClO4, and H2SO4, first ionization step. Strong bases are, as you recall, group 1A and group 2A hydroxides. Now, characteristically, these ionize 100%. That is, you will not find any molecular forms of either strong acids, strong bases in solution. Now, this analysis of this analytics, you can go direct to the KW hydronium ion and sulfur H minus, because the ionization of the acid, if you have HCl 1 molar, it's going to deliver 1 molar in hydronium ions, and typically we add to this calculation a pH calculation minus log of the hydronium ion concentration, or POH equals minus log of the hydroxide ion concentration. So that's what we've covered so far. Now, to contrast this, we talk about the weak electrolyte ionization and weak acids and weak bases. We've learned that a weak acid is identified because it is not a member of the strong 6. The strong weak bases are typically ammonia and ammonia derivatives in water. So we want to see how these evolve and are used in calculating pH and concentration value. Weak electrolytes in general do not ionize 100%. Most of them will ionize about 1 to 2%. If we take a weak electrolyte, hypothetically, HA, could be acetic acid, benzoic acid, or whatever acid, then we know that this will ionize into H plus and anions, a conjugate base like this. So, but what you need to understand about this, the anion in here, this has a strong attraction for H plus. That's why it's a weak acid. The anion bond in here is very strong compared to, say, the strong acids. So as it delivers in the first few seconds, the concentrations of hydrogen may be coming up, and the concentrations of the anion, I'm going to do it just like this, H plus, A minus. As these concentrations increase, what happens is this begins to attract that hydrogen with a great deal of force. And so these recombine, let's combine, C-O-M-B, recombine to form HA again. And so the reaction reverses itself. So while we reach this point very quickly, it continues, the weak electrolyte continues to deliver hydrogen and anions into solution, but at a certain concentration of anion and hydronium ion, they start recombining and shifting back the other direction. So this is the empirical reason why weak electrolytes perform as they do and have limited ionization, degrees of ionization, like this. So again, this is an explanation of why it has about a 1 to 2% ionization. I will show you the analytics of weak acids. We're going to determine the pH, pOH, and hydronium and hydroxide ion concentrations of a weak acid. Let's say we're given a 0.10 molar acetic acid solution. Determine hydronium ion concentration, the hydroxide ion concentration, the pH, and pOH of that solution. Now, one thing that's given also is what we call an acid ionization constant. Ka equals 1.8 times 10 to the minus 5. No units are needed, but that has to be given. Okay, so in working with weak electrolytes, you cannot assume that a 0.10 molar HOAC solution yields how many molar in hydronium ions. You don't know what this is. You cannot assume not equals to 0.10 because of limited ionization. So what we have to do in working with the weak electrolytes like this, you have to use the ICE table and fill it in and use the equilibrium row to calculate the hydronium ion concentrations. So it goes a little bit like this. Like if you have HOAC going into solution partially, like this, then it's going to reverse itself very quickly, as I explained in the last slide. And you got to see initial change in concentration at equilibrium. So we're starting with a 0.10 molar solution, and like I say, consider this in the a horse race, where you have 0 and 0 at the outset of the ionization. Then we allow the gates to open, the ionization to occur. This decreases by the coefficient times x increase and increase by x, and at equilibrium we have 0.10 minus x, and x, like that. And then you should be able to understand what I've done up to this point. Now there's one consideration that you need to note is 0.1 minus x in the compound, right here. The question is, can I drop the x? Is it insignificant, or is the x not insignificant? Well, there's a thing called the simplification test. If the Ka, let's see, if the concentration divided by the Ka value is greater than 100, then drop the x in this first column, and you won't have to put that into your calculation. So if the Ka value for this is 1.8 times 10 to the minus 5, and we have a 0.1 molar, then 0.10 molar divided by, well, 10 to the minus 5. Let's just keep it at that. Gives you 10 to the minus 1 over 10 to the minus 5. Sorry about that. Okay. Ta-da. So this is going to give us 10 to the fourth power, which of course is much greater than 100. Therefore, drop the x on this portion. So this will become 0.10 molar in that row. So it's just a quick way to determine. There are problems that you will see, and if it does not conform to this, you'll have to use the quadratic formula. I'll try to work one of those today as we get deeper into this. Okay, so here we are at this equilibrium row, and we need to determine the hydronium ion concentration, the hydroxide, and now in this is in pure water. When this ionizes, it's going to deliver hydronium ions, but the acetate ions in the same concentration. So hydrogen and acetate will be equal in the pure water ionization. So to determine the hydronium ion concentration, we'll use the Ka expression for this equation. Product concentration of the products divided by the product concentration of reactants raised to the coefficient powers. Well, everybody's 1, so it's hydronium ion times the acetate ion concentration divided by excuse me, HOAC concentration. And we insert the equilibrium row into this expression, and that gives you x times x divided by 0.10, and that's equal to the Ka expression, 1.8 times 10 to the minus 5. Like this. And then we solve this, it becomes x squared over 0.10 equal 1.8 times 10 to the minus 5, and this gives x to equal the square root of 1.8 times 10 to the minus 5 times 0.10. Now, x, of course, is the hydronium ion concentration, as we see up here, and so x also equals that expression right there. And if you look closely at it, it is the square root formula that I gave you in the last sections, in that hydronium ion for weak electrolytes is always the square root of Ka times whatever the original acid concentration is. And so this is really where it comes from. So it's a shortcut for any of the weak electrolytes on the acid ionization table. Well, this turns out to be 0.0012 molar in hydronium ions. Yeah, make that 1,3 in the hydronium ions. So we now have the first question answered. What is the hydronium ion concentration? Now, in pure water, honestly, you do not have to go through this. You can just go right down here to the square root formula, calculate the hydronium ion, and you're through with it. Well, at this point, everything kind of reverts back to what we covered in the last sections. You have calculated the hydronium ion concentration is 0.0013 molar. Then you can use the Kw expression solve for the hydroxide, divided kW over the hydronium ion. So the hydroxide ion concentration in our problem is 1 times 10 to the minus 14, and it'll be on your reference sheet. And the hydrogen is 0.0013, and everything's going to come out in moles per liter. I get 7.7 times 10 to the minus 12th molar in hydroxide ions. And that one. Well, pH and pOH follow very quickly. pH equals minus log of the hydronium ion concentration, which is 0.0013. .89. Weak electrolytes, weak acids, typically run in the pH equal 3 range. In the strong acids, you'll find them further down the chart around pH of 1 in a general consideration. Well, if you have the pH, remember that pH plus pOH always equals 14, and from that you can get the pOH to equal 14 minus the pH value. So pOH now is 14 minus 2.89, giving 11.11. And you can add these two together to see that you added or subtracted correctly, and it'll give you 14. So that's the essence of what you're facing right now. Okay, let's say you're given cyanic acid, HCN, and its Ka value is here it is. It's hydrocyanic acid, 4.9 times 10 to the minus 10. Calculate hydronium ion concentration, hydroxide ion concentration, pH, and pOH. So this is kind of condensing it down to the shortest possible route from start to finish. Where do you start? You start with the pH. Well, this being a weak acid, of course, you don't need this, but I'm putting the ionization in here anyway. Like that. So calculating the hydronium ion of a weak acid, you have to use the square root formula. So that would be the Ka value times the concentration of HCN. Let's say we have a 0.25 molar HCN. Forgot that part. Let's put that in there. And so the hydronium ion would be 4.9 times 10 to the minus 10 times 0.25. All comes out in moles per liter. Punching that into your calculator, and you're through with the hydronium. I get in my calculator 0.11 times 10 to the minus 5 molar in hydronium ions, right there. So next one would be the hydroxide ions. You know it's going to come from the Kw expression, so it'd be Kw over the hydronium ions. If you were looking for hydronium ions and having the OH, it'd be Kw over OH. So in this case, it's 1 times 10 to the minus 14 over 1.11 times 10 to the minus 5. Everything's going to come out in moles per liter. 9 times 10 to the minus 10. So in OH ions, right there. And then finally, you have the pH being minus log of the hydronium ion concentration. It'd be minus log of 1.11 times 10 to the minus 5 gives us 4.96. And finally the POH, 14 minus pH, 14 minus 4.96, 9.05. Well, actually 4, 6, 10, 10, 9, 10, 11, 12, 13, 14. Okay, so we've got all of the specific items that you would need in a weak acid calculation in this context. So is referred to as polyprotic weak acids. Polyprotic weak acids mean that the compound contains more than one ionizable hydrogen. Say HOAC is a monoprotic weak acid. If you have H2CO3, this is a polyprotic or a diprotic acid. And then you have those like H3PO4, triprotic acid. Now, those with the diprotic and triprotics or tetraprotics or whatever polyprotic structure you have, these ionize one at a time, and you have to calculate their hydronium ion concentration for each individual ionization. For example, we'll start with carbonic acid here, H2CO3, and it has two hydrogens, which means that it has what they call a Ka1, and which is, let me give you the number, 4.3 times 10 to the minus 7. And I'll put it down here, Ka2, and that one is 4.8 times 10 to the minus 11. Now, get that jotted down. Now, what I want you to focus here for a second is look at the size of the first ionization step. It's 10 to the minus 7, and the second one's 10 to the minus 11, a significant drop in magnitude of the K value. Well, what does that mean? That means this second ionization will be HCO3 minus ionization. This is the first ionization off of the carbonic acid and HCO3. That means that H on the carbonic acid bicarbonate ion is strongly bound to the CO3. It's more strongly bound than the first hydrogen is to the carbonic acid structure. And I'll show you how that works. Okay, carbonic acid has a structure in Lewis structure form, looks like this. Those are non-bonded electrons, all the dots and stuff, like that. And so it has two ionizable hydrogens. Well, in the first ionization step, it will go to this structure and deliver one of the hydronium ions into solution. Now, this formal charge increases strength of hydrogen-oxygen bond on other end of molecule. So this right here is negative, is acting to pull that hydrogen in even tighter to the oxygen that it is bound to here on this end of the molecule. So when you go to the second ionization step, I'll draw it, yeah. It will ionize to give you the hydronium ion, but this will be even smaller overall, harder to ionize. Has two negatives on that. So this is very hard to remove in the second ionization because of the strong bond. So I just want to emphasize that idea that the first ionization step functions to make the second ionization much more resistant to ionization than the first ionization step. And this will play a big part in a moment in your calculation sequence. So, working with the hydronium ion concentration from the first ionization step, you want to start with the equation of one ionization, that is one hydrogen coming off of the carbonic acid, like this, H2CO3. It's all an aqueous solution. Set that up as an equilibrium to deliver 1 mole of hydronium ions plus the bicarbonate ion HCO3, like that. And then build your ice table around this. Initial change in concentration and concentration at equilibrium. So indicating a 0.1 molar solution to start, and 0 and 0 as we have in the past. The ionization would reduce the concentration of the carbonic acid by X and increase the hydronium by X and the bicarbonate by X, leading to 0.10 minus X, X, and X. Now, the question is, can we drop the X? Well, just eyeball it. Here's 10 to the minus 7 divided into 10 to the minus 1. Is that greater than 100? That's all you got to do. Would you think that 10 to the minus 1 over 10 to the minus 7 is greater than 100? So yes, we can drop the X and the end of this position right here. Does everybody understand what the little test to remove it? Okay, so then we can say that this X is so small that it will not significantly affect the 0.1. It'll be in the 10 to the minus 5 range. If you get 10 to the minus 5 here in the X subtracted from 0.1, you made little or no difference at all, is the point I'm trying to make to you. So you have 0.1, then X, and X. Now, at this point we set up the Ka1 equilibrium expression because this is the first ionization, and that would be the hydronium ion, bicarbonate ion, divided by the carbonic acid we started with. And of course that is X times X over 0.10, and that's X squared over 0.10. So solving for X in here, we have 0.10 square root of times the Ka1. I just do that for emphasis. You'd probably shortcut it anyway. And so the square root of 0.10 times 4.3 times 10 to the minus 7 gives us our hydronium ion moles per liter from the first ionization step. So we have a 2.1 times 10 to the minus 4, y'all check me on that, for the hydronium ion from the first ionization step. Okay, we're fixing to do the hydronium ion from the second ionization step. Now watch this closely so you won't get confused on the second ionization step. The rule here is whatever the concentrations are at the end of the first ionization step, listen to me carefully, whatever the concentrations are at the end of the first ionization step are the concentrations of the compounds and ions in the beginning or initial step of the second ionization step. That is, the second ionization step will be the bicarbonate ion, ionizing to the, delivering its hydrogen, and then CO3 to minus. Well, the initial concentrations, okay, would be, and we're still at 0.1, right there. And the hydrogen is 2.1 times 10 to the minus 4. And so whatever the carbonic acids you started with and the hydrogen, you put those two down. And the unknown will be over here. The unknown, would, whatever that comes out to be, will be the amount of the second that comes out. Now another outcropping of this is it is assumed that all of the ionizations all the hydrogen comes out of the first ionization step. You'll see how this works in here in just a second. Now it may be confusing right now, but hopefully I can clear it up here in a second. Complete your ice table like this. This goes down by X, and we have 0.10 minus X, and yes, you can drop X here, 0.10 molar here, and this is 2.1 times 10 to the minus 4. Oh, I'm sorry, my bad. This is 2.1 times 10 to the minus 4 molar in the bicarbonate. I'm sorry about that. I'll explain. The outcome, if we determined the X to be 2.1 times 10 to the minus 4 from the first ionization step, well, those are equal. And so the bicarbonate, being the second ionization step, is 2.1 times 10 to the minus 4. I just got senior moment, sorry. Anyway, that's what I'm talking about here. Whatever's at the end of the first ionization step starts the second ionization step. So when we get this to 0 over here, this minus X, I'm not at the end yet, plus X. Now, the amount of X that's going to be delivered in hydroniums from the second ionization step will be equal to the amount of X delivered in the carbonate. Well, that's going to be a remarkably small number. Try to add to the hydronium here. So that's why I say all of the hydrogen comes from the first ionization step. So this is 2.1 times 10 to the minus 4 plus X, and then X over here. Let's see if I can get that cleaned up. And that's so small that we can say this is all that's there, this like that. Okay, so X will be the amount of hydrogen delivered as well as the carbonate delivered. Well, when you set up the Ka2, I said there was a little neat little twist in this. It comes out of this. It's the equilibrium expression is H plus CO3 minus 2 over H CO3 minus. So when you substitute the values in the equilibrium row into this expression, you have 2.1 times 10 to the minus 4 times x divided by 2.1 times 10 to the minus 4. And so you notice that the 2.1 times 10 to the minus 4 on the numerator will cancel with the 1 on the bottom. And I'll show you. And this ultimately equals whatever this x is, and x is equal to Ka2. And that's true for all the diprotics in fresh water. That is, the second ionization Ka value for the carbonic 4.8 times 10 to the minus 11. So Ka2 is equal to 4.8 times 10 to the minus 11 is also, and if you put that in molar terms, that's also the CO3 2 minus, and is equal to the amount of H plus delivered from second ionization. From the second ionization step. So what we're looking at here is, when you talk about, this is from the first ionization step, is 2.1 times 10 to the minus 4, and then you add to that 4.8 times 10 to the minus 11. How much of a change is that going to be when you add 10 to the minus 4 and 10 to the minus 11? None. So when we consider a polyprotic ionization, you don't have to you don't have to go through the second ionization step, because it's not going to make a contribution to the overall hydronium ion. So the conclusion here is, it is generally assumed all H plus ion concentration comes from the first ionization step. Now I'm going to rework a second one here in a minute, and I'll show you how to condense all this stuff down. The second thing is, in the quantities delivered in the second ionization step, molar concentrations of the cation and anion equal Ka2. You don't even have to calculate it. In the course of the calculations. Now I know this seems like a just kind of like throwing mud in your face, so to speak, but I'll show you how to condense it all down and hopefully make it simpler in the next problem. Okay, we're given hydrogen sulfide, a 0.05 molar solution with Ka1, Ka2 given as shown, and you're to calculate the hydronium ion, hydroxide ion, pH, and pOH of the solution. Of course, it's a diprotic ionization, and so you know it's going to deliver hydrogens from the first ionization, then hydrogens from the second. And the idea is to determine, I'll put in HS ions and sulfur 2 minus concentrations. So that's just everything you can calculate in this kind of problem. Okay, start with, in the first ionization step, to determine hydrogen and the HS concentrations. That's for the first ionization. Use the square root formula. You don't have to go through the ice table. Just use the H plus will equal HS, which equals the square root of the concentration, or Ka1, times the concentration of H2S used, like this. And so that would be 8.9 times 10 to the minus 8 times 0.05. Take the square root and express it in moles per liter. And I'll take care of those two. You don't have to go through the ice table. So I have 6.7 times 10 to the minus 5 molar in hydronium ions and bisulfide ions. So you're through with that one. So that's calculation A. So calculation B would be the second ionization step. Hydronium ion plus the sulfide ion concentration. Well, to get the amount of hydrogen delivered from the second ionization step as well as the sulfide, all you have to do is look at the Ka2, because the hydronium ion delivered in the second ionization state will equal the sulfide delivered, and that's equal to Ka2, and that's equal to 1.2 times 10 to the minus 13 molar. So you've got the second ionization, but you also have the sulfur from the second ionization step, which is this concentration. So the hydronium ion and the ion in lowest concentration is always the Ka2 expression, Ka2 value. So we have this, and really that, and taken care of that and that. We got the hydronium ion. So all we need is this and the hydrogen and POH. Now, looking at the hydrogen from the second ionization step in the 10 to the minus 13 range is what's delivered in the second step, added to the hydrogen from the first ionization step, which is 10 to the minus 5. So it's not going to make any difference in increasing the hydronium ion. So that's why I say all hydrogen comes from the first ionization step. So when you calculate pH, you'll calculate it based on the first ionization step hydrogen. I'll say it again. Use the first ionization hydrogen for your pH in a diprotein or polyprotein. So, see, for pH, assume hydrogen ion concentration is from first step. So pH now equals minus log of the hydronium ion concentration from the first ionization step. 6.7 times 10 to the minus 5. I get 4.2. So there's your pH of that ionization. POH is 14, and the POH would of course be 14 minus the pH, 14 minus 4.2, and you're through. And so, as you look at this problem, the first ionization step, use the square root formula. Second ionization step, just equate the hydrogen and the anion by itself to the Ka2. For pH, assume all hydrogens from the first ionization step and calculate it as you have in the past. And so using the first ionization step, you see these two, that's where you get it. And then for your POH, subtract your pH from 14. You see those 4 steps in there? 1, 2, 3, 4. And so if you practice it a little bit, they got some more diprotics, and then make up your own concentration and practice through it. But you don't have to go through all the complexities that I used in explaining through the ice tables. Okay. We've looked at weak acid ionization. And we've looked at diprotic or polyprotic acid ionizations. And what you need to do is sort out in your mind what you need to use in the analytical end of this. Now, the acid ionizations up here are exclusively hydronium ions, which is the square root formula. Like that. So that will lead you to the hydronium ions, and you can calculate the hydroxide ions using the Kw expression after that. In the diprotic acid ionizations, for the first ionization step, use the square root formula. And so that'll give you your hydrogen. You can go and get your OHs and stuff. Now, don't forget, maybe you have or not, but the hydronium ion concentration, once you get that, is always equal to 10 to the minus pH. So this is a little formula you want to kind of keep in the back of your mind in terms of calculating. It might give you a pH and all you have in a problem, and all you have to do is take 10 to the minus pH and you'll have your hydrogen. You don't have to go through a lot of other calculations. So this is kind of a sidebar formula that you can use to shortcut other problems. In the second ionization step, really you don't consider the second ionization hydrogen because it's so small it doesn't contribute. Everything's assumed to be from the first one. The only thing that's important in the second ionization step is the anion, and it's the ion in the lowest concentration. And that's always equal to Ka2 expressed in moles per liter. So these are some factoids that you need to keep in mind as you go through future problems and things, and it'll simplify a lot of what you're dealing with. Now, the pH and pOH and hydroniums and hydroxides are calculated in the past using the Kw expressions and the minus log of hydrogens or whatever you need. Okay. Now, when we talk about weak base ionizations, we first need to realize what a weak base is and what is the reaction for a weak base ionization. You don't have the multiprotic or multi-hydroxide structures in these ionizations. You only have one ionization. So a weak base, as you recall, is an ammonia or ammonia derivative and water. Okay, ammonia, as you recall, is this, and when we put it in water, the electron pair has a strong affinity for one of the hydrogens from water and will produce an ammonium hydroxide by absorbing one of the hydrogens and becoming NH4. See, we've increased the 3 to 4 now. And then you tag it with an OH. And this is your cation, the NH4, and your hydroxide. And this will ionize to the ammonium ion and the hydroxide ion. This is your weak electrolyte ionization. However, on tests, they'll give you a list. It says which of the following is a weak base. Well, they will not give you the ammonium hydroxide. What they'll put in there is the ammonia or ammonia derivative, whatever it is. So if you see an amine, or which is an ammonia derivative, amines, that's a class of compounds that are ammonia derivatives. Amines in water, they'll just write that. They won't put the OH in. Now, but when you analyze this and apply the analytics, you will apply it to the ammonia ionization, and everything follows straight away from that. And remember, in the weak bases, the square root formula delivers the OH, and the acids, it delivered the hydronium ions. So our first problem is calculate, or let's just say we're given, let's start that way, given 0.10 molar NH3 aqueous, Kb is equal to 1.8 times 10 to the minus 5. Same thing as acetic acid, but like that. Calculate OH, hydrogen, pH, POH, anything else you can come up with. Okay, as I indicated earlier, this is evaluated from the ionization of the ammonium hydroxide. So what I'll do is start with that ammonium hydroxide, but keep in mind the ammonia and water goes to this first and then ionizes to the ammonium ion and the hydroxide ion, like that. Then you set up your ice table and you put in your data, minus x, x, x. We have 0.10 minus x. And the same principle applies if you take concentration divided by the Kb value. This, if it's greater than 100, you can drop the x. So yes, we can drop the x in this problem. Then apply to determine what x's are, the ammonium and hydroxide. You use the Kb expression, which products over reactants. And then substitute your equilibrium row into your Kb expression, and that'll give you x squared over 0.10 to equal 1.8 times 10 to the minus 5. And of course, solving for the x will give you the hydroxide ion concentration as well as the ammonium ion, which is not going to affect the pH or anything, is the square root of the Kb times the base concentration. So you see where the hydroxide uses the square root formula, just as hydronium ion uses the square root formula for the weak acids. And so this becomes 1.8 times 10 to the minus 5 times 0.10 square root of, and that's 0.0013 molar in hydroxides. I choose that because it's simpler. Like that. From there, you can get the POH, then the pH as you need. So POH would be my first guess, which would be minus log of 0.0013. I forgot what that is. 2.89. And then your pH will follow as 14 minus POH, 14 minus 2.89. 11.11. And so you quickly go through these using the square root formula for the first ionization. You deliver hydroxides because it's a weak base. Then you can calculate your pH, pOH. Now, if you want to go ahead and get your hydronium ions, just go 10 to the minus pH, which is 10 to the minus 11.11, and you won't have to go through the kW expression. Just another way to do a problem. 7.7 times 10 to the minus 12. Just punch it into your exponential portion of your calculator. Okay, so setting up the ice table, we start out with 0.0036 molar, 0 and 0, and so minus x plus x plus x, and so we have 0.0036 minus x, x, and x. Now the question is, in this problem, can I drop that x? So how did I tell you to figure it? Well, its concentration over the K value has got to be greater than 100. So this is 0.0036 over 3.3 times 10 to the minus 4. And what does that give us? Let me just mark that out. That gives me 11. Well, what does that mean? Well, it's less than 100 to start with. So, because of this, cannot drop X in the equilibrium row. Therefore, must use quadratic equation. For H plus. I'll show you how that works out. Everything out except the equilibrium row. Leave the equilibrium row, and Ka is equal to 3.3 times 10 to the minus 4. And we know that we can't drop the X in this, so what does that leave us with? So if I set up the Ka expression, products over reactants, I'd have hydronium ions, anion over the HACS. Like that. Of course, that's x squared over 0.0036 is equal to the Ka value, 3.3 minus x. Stretch that out a little bit so it looks better. Right here. So with this, we can't drop this, so what we're winding up with is a quadratic. And the formula is shown here. Putting that in quadratic form, I multiply both sides by the 0036 minus x, so I'll have x squared to equal 3.3 times 10 to the minus 4, 0.0036 minus x. Like that, and I distribute, I have x squared, run that out. And that's 1.1 3.19 times 10 to the minus 6 minus 3.3 times 10 to the minus 4x. And then I'll set it up as a quadratic equation, the polynomial, or minus 1 point. I'm going to do this a little bit different. Plus minus 1.19 10 to the minus 6 to emphasize certain things. Oops, got the wrong one. Wait a minute. This would go over as a plus 3.3 times 10 to the minus 4x plus a minus. That's what I want to do. 1.19 is 10 to the minus 6. And all of that equals to 0. And so you see the polynomial. Now we'll solve it for x using the x equals minus b plus or minus the square root of b squared minus 4ac. It's not as bad as it looks, it's just busy, over 2a. So that's your initial setup here. And so you identify a is 1, b is 3.3 times 10 to the minus 4, and c is a minus, that's why I put it in parentheses, is a minus 1.19 times 10 to the minus 6, and we substitute and solve for x. So I'll bring this down here with a equal to 1, b equal to a plus 3.3 times 10 to the minus 4, and c is equal to a minus 1.19 times 10 to the minus 6. So now x, which is of course the hydronium ion concentration, minus 1.19 times 10 to the minus 6 here, plus or minus square root of 1.19 10 to the minus 6 squared minus 4 times 1. C is I keep messing up, I keep picking up the wrong number. My apologies. Dang it. Minus 3.3 times 10 to the minus 4 plus or minus the square root of 3.3 times 10 to the minus 4 squared minus 4 times 1 times 1.19 times 10 to the minus 4. That's a negative in there. Goes in here, and all of that's a square root over there. Running out of room. Over 2 times 1. So let's simplify the square root first. So that would be a minus times a minus gives us a plus. So that's convenient, and then we'll add back this. So 1.19 times 10 to the minus 4 times 4 equals that. Add 3.3 times 10 to the minus 4. Nope, I got to square it first. Okay. Store 1, and then 3.3 times 10 to the minus 4 squared plus, we call 1 equals, and take the square root of that. Okay, so now I have 3.3 times 10 to the minus 4 plus or minus 2.2 times 10 to the minus 2 over 2 times 1. Okay. Now, in these calculations, you have option to get 2 answers out of it. Always choose the positive value. So you wouldn't use the minus 3.3 times 10 to the minus 4 minus 2.2 10 to the minus 2. You would take 2.2 times 10 to the minus 2 minus 3.3 times 10 to the minus 4 over 2. So that essentially is a plus 2.1 or 2.2, well, 17 times 10 to the minus 2 over 2. And I get 1.1 times 10 to the minus, or 0.011 molar in hydronium ions. So using the quadratic, we just work right through it, and we get that kind of value. Of course, pH minus log of the 0.011, and that's 1.9 or 2.00, like that. And you can go and calculate all the rest of it using the formulas we've had in the past. So I've given you all of the possibilities for the weak electrolyte ionizations. Okay. In order to understand how this works, you need to understand what the 4 acid-base titrations are, and they're very simple. You have a strong acid, strong base titration. You have a weak acid, strong base titration. You have a strong acid, weak base. And then you have weak acid, weak base. Type titrations. Examples, let me give you those. We did the HCl, NaOH type titration reaction. Then you would have an acetic acid, or a weak acid with a weak acid ionization and a strong base. Then you would have a strong acid and weak base, ammonium hydroxide. And then you would have a weak, or acetic acid and ammonium hydroxide. Like this. Now, the point of this is that when you react an acid and a base together, you always get a salt of that acid-base combination and a weak electrolyte driving force. And for the most part, in these type of reactions, and I'm using as illustrations, the driving force will always be water on the end. For example, HCl plus NaOH, double replacement to generate sodium chloride, the salt, plus H2O. And in the second case, acetic acid plus sodium hydroxide would also generate a salt, sodium acetate, plus water, and so forth. So we can go through each one of these and show how the acid plus base gives us salt and water. Or say at equivalence point, we have for a strong titration, you will see a graph that will go say something like this. And the equivalence point will be at pH of 7, like this. And this would be a strong, like that. And for a weak strong, you'll see it'll start a little higher, and the slope will go up like this, and finish in that way. But the equivalence point will be approximately, say, at 9. This is a weak acid, strong base titration. For a strong acid, weak base titration, you'll find the equivalence point will be in this acidic range. it'll start off in here, go up, and the equivalence point back over here will be about a 4. Now, the weak acid, weak base titration is dependent on who has the larger K value in that. So we're not going to put that one in this set. But what you need to understand is in the titrations, the equivalence points here, here, and here are a result of hydrolysis of the salt. Now, just as generalizations, the salt that's generated in a strong hydrolysis, the ions do not hydrolyze. There's no hydrolysis here. And I'll show you in a minute. In the weak acid, strong base, the hydrolysis is the anion. And this leaves an excess hydroxides. And so that's kind of a generalization for the weak acid, strong base. Whereas in the strong acid, weak base, it's the cation hydrolysis that causes the pH to drop. Gives an excess of hydronium ions. So what I'm doing is kind of giving you a sneak preview of how the analytics will work out as we go through each one of these types of calculations. Okay, so we're going to use a strong acid, strong base, hydrochloric acid, for example, and sodium hydroxide, as you know, goes to sodium chloride plus H2O. Now that's the acid-base reaction, or reaction 1. That's the standard. Now there'll be 4 reactions in here that we will take a look at. The second reaction is the ionization of the salt. So salt, of course, is a sodium chloride, and it ionizes 100% to sodium and chloride ions, like that. Now what you want to do after that salt ionization is test each ion reaction with water. That's called hydrolysis. The reaction with water is the hydrolysis. So we'll use the cation first. Sodium plus H, and I'm going to separate it like this for a reason. This is the plus component of water. Of course, this is the negative component of water. So the plus theoretically attracts the negative, and so theoretically you have a sodium hydroxide plus an excess of hydronium ions. See what I did on that? Then the fourth one is testing the chloride with water. It's negative, so in the same context, say this is plus against a minus. This would give an HCl plus an excess of hydroxide. Now the problem with this is both the HCl and NaOH are strong electrolytes. And these prefer to remain 100% ionized. Therefore, we conclude that no reaction occurs or no hydrolysis occurs. And as a result, the pH at equivalence point. Now, once the reaction is completed you only have, at the equivalence point, you only have sodium chloride. We haven't gone past that. So you're talking about only sodium chloride present, and it's the ions from that react with water, or may not react in this case. So the pH at the equivalence point depends only on autoionization of water. And we've seen that equation before. Now, the analysis of this is how much hydrogen, how much hydroxide is generated in the autoionization. Well, for pure water, ionization will give you 10 to the minus 7 molar in hydronium ions, and the same amount in hydroxide ions, like that. So if we're going to calculate the pH of that, minus log of the hydronium, that'd be minus log of 10 to the minus 7, which of course gives you 7. So that is the rationale behind why is that a strong acid, strong base, always 7. So if you recognize, you know how to identify strong acids, the strong 6, reacting with strong base, group 1, group 2 hydroxides, except beryllium hydroxide, then you know it always winds up at equivalent point of 7 pH. And this is the reason why, because the ions generated in the salt do not produce any weak electrolytes over here. So when you are studying these, I'll show you how to differentiate as we go along. Once you see those, you say no reaction, and whatever's left is what affects the pH. Now this is where it gets kind of gnarly a little bit in the calculations. Weak acid we're going to use is acetic acid and sodium hydroxide. And again, it goes to the salt and water. Well, what's the salt? Well, sodium acetate. It's the cation, anion, and then water. So we have sodium, OAC, and then H2O. So that's reaction 1. The second reaction in the analysis here is the salt ionization. So we want to take NaOAC. All salts ionize 100%. Now, not all salts have the same solubility. We'll learn that in the next chapter. But whatever does go into solution ionizes always 100%. So we have sodium ions and acetate ions in that solution at the equivalence point. At the equivalence point, we don't have anything else yet. At any rate, the third and fourth are testing the ion reactions with water. That's the hydrolysis. So we'll take the cation, Na plus H2O, and we'll look at it. Well, that's going to give a sodium hydroxide plus H plus. And then the acetate, OAC minus plus HOH, of course that's the plus, and that's the minus, like that. And so minuses attract pluses, so this gives you an HOAC right here, plus an excess of OH minus. Now does that make sense, guys? You following through? I know I'm scooting through this pretty quick, but hopefully you're understanding how I'm getting these 4 reactions. That's very important, because the one you really want to get to is this fourth one right here. Why would this number 3 not be important? It's because it generates a strong electrolyte. So this one is a no reaction. So the sodium ion does not have any influence on the pH. However, the acetate ion down here, reacting with water, generates a weak electrolyte. How do you know? It's not a member of the strong 6. And the resulting excess hydroxide is the reason the pH is affected, and it shifts up. As you showed you, a weak acid, strong base titration is in the base range. Now, this is the equation we will use to analyze what's going on. Let's say that in this reaction you generated a 0.10 molar acetic acid. We'll make that assignment. Well, in this hydrolysis reaction that I'm showing, you set up an ice table, just like we did in the other analysis. So if you followed me down through the one you will analyze is the reaction that does produce the weak electrolyte. When we do the strong acid weak base, it's going to produce a salt over here of ammonium chloride and leave an excess hydrogen. That's the one you want to analyze, but the chloride will not react because it has an HCl. You'll see that in the next example. So let's assume that we have this salt, and well, when this ionizes, it's going to leave 0.10 molar here, and that one's going to be 0.10 molar also. So we bring that down here, 0.10 molar. Everybody following me so far? Okay. Disregard water, and this before it reacts with water, of course, the initial row is 0. And then we allow the horses to run, open the gates, let the reaction go. This goes down by X, this goes up by X, and X, disregard water, and 0.10 minus X. In all of these, you can drop the X. The thing you'll need is the Ka value for the HOAC. I'll show you in a minute. So this is the equilibrium row for this analysis. Is everybody still with me?